Hello, welcome to this MEI M1 revision video where we're going to be looking at velocity time graphs and kinematics. This is June 2011, question 7. So let's have a look through the question first. We're told that a ring is moving on a straight wire and it has a particular velocity v after a certain number of seconds t. Now we're told that we have one model, model A, for the motion of the ring, which gives us this velocity time graph that we've got here. So we notice that we have some times when the velocity is positive and sometimes when it is negative. So we have to use model A to calculate the acceleration of the ring when t is 0.5 and the displacement of the ring from Q, which was the starting point, when t is 2 and when t is 6. So that's 2 marks and 5 marks for those. We're then told that there's an alternative model, B, where the velocity of the ring is given by this expression here in terms of t, and we have to calculate several things. So we have to calculate the acceleration when t is 0.5, 3 marks. We have to work out by how much the models differ in their values for the least v, so the smallest velocity, within this time interval 0 to 6, 4 marks. And then we have to calculate the displacement of the ring from Q when t is 6, as given by model B, which is this one here. So let's have a look at the graph again, and we have to calculate the acceleration of the ring when t is a half. Now if you remember, for a velocity time graph, the acceleration is given by the gradient of the graph. So what we need to do is identify where t is a half, which will be roughly here, and we need to find the gradient at this point. Now that gradient is constant, so we can have a look at two convenient points where we can find the gradient, and I'm going to choose here and there because that makes it nice and easy to find the gradient. So we look at the change in y, that is 0 minus 20, and the change in x, 2 minus 0. So we get minus 20 over 2, which is minus 10. In other words, it is decelerating. So that's 2 marks. We now have to work out the displacement of the ring when t is 2 and t is 6. Now on a velocity time graph, anytime we see the word displacement, we need to be thinking about the area under the graph. Now when t is 2, that's relatively straightforward. I'll just go back to the graph. When t is 2, we can see that this is the relevant area here, and that is all positive. The velocity was positive, so it was going all in the same direction. And so all we need to do is find the area of this triangle. Base is 2, vertical height is 20, so it's a half times 2 times 20, which is 20 meters. Now when t is 6, it's slightly more complicated. Again, if we go back and look, we have a positive area here and a positive area at the right hand side, but here we have a negative area. Now this represents where the particle or the object is moving back towards its starting point before starting to move away from the starting point again. So the actual displacement needs to take account of direction. And so we need to think that any areas above the axis we are thinking of positive, it's moving away from the starting point, and anything below the axis is negative, it's moving back towards the starting point. So I'll consider this in 3 sections, 2 triangles, both of which are positive, and a trapezium here underneath, which is negative. So the first triangle is the same as the previous part of the question, and this triangle here has got a base of 1 and a height of 8. So if we look at the positive areas first, we've got, same as we had last time, half times 2 times 20. And then we've got a half multiplied by 1 multiplied by 8. So that's 4. So that gives us a total of 24 meters where it's moving away from the starting point. And then we need to have a look at the negative section where it's going back towards the starting point. And if we remember the formula for the area of trapezium, we need to work out A and B and H. A and B are the 2 parallel sides, so the bottom side here, or top side, whichever way you think about it, is 2 to 5, so that's a length of 3. And then this side here has got a length of 2.1, the difference between these two values. The vertical height is 4, and so we're going to have 3 plus 2.1, the two parallel sides, multiplied by 4, and that gives us 10.2. That's negative, so the overall displacement will be 24 minus 10.2, which works out to be 13.8. Now we move on to this alternative model B. We're given a velocity and we're asked to calculate an acceleration. Now you may remember something like this, where if we're going from displacement to velocity to acceleration, we differentiate, and if you're going the opposite way, you would integrate. So here we've got velocity and we want acceleration, so we're going to differentiate. So the acceleration is the derivative of the velocity, and that works out to be 4t minus 14. Now we're asked to find it when t is 0.5, so it's 4 multiplied by 0.5 minus 14, and that works out to be minus 12 in this particular model. For part 4, we have to work out by how much the models differ in their values for the least velocity in the time interval. Now if you remember back to the graph for model A, the lowest point was here at minus 4. So the lowest velocity, minus 4, and we can see that from the graph. For model B, we know that this is a quadratic, and it's positive quadratic, and so we know the minimum value of v will be at the minimum point of the graph, and that is when the acceleration is equal to 0. Now we worked out the acceleration in the previous part of the question was 4t minus 14, and so if we solve that, we get t is 3.5. So we know that the minimum occurs when t is 3.5, and if we substitute that back into the equation of the curve, the equation is 2t squared minus 14t plus 20, and so substituting in 3.5, that works out to be minus 4.5. The question actually says calculate by how much the models differ in their value for the least v. So we can say model B is less by 0.5 meters per second. Moving on to the final part of the question, we have to calculate the displacement of the ring when t equals 6. Now going back to what we were talking about earlier, if you know velocity and you want to know displacement, you need to integrate. And we know that we want the displacement from when t is 0 to when t is 6. So we can think about this as a definite integral from 0 to 6. This was the expression for the velocity. And so if we integrate that, we get 2t cubed over 3 minus 7t squared plus 20t, and that's between 6 and 0. So substituting in the values, we'll get 2 times 6 cubed over 3 minus 7 times 6 squared plus 20 times 6, and then if you sub in the bottom limit, you're going to get 0 in each term. And working that out on a calculator gives us an answer of 12 meters. So let's go back and have a look at where the marks were allocated in each part of the question. So going back to part 1, for finding the acceleration, you got a method mark for showing that you were finding the gradient, and an accuracy mark for correct answer only there for getting that correct. Moving on to the next part with the displacement. For t is 2, you got a method mark for aiming to find the area of the triangle, and an accuracy mark for doing it correctly. There's then an independent mark for finding the area of the smaller triangle at the right hand side. Another for finding the area of the trapezium. And then a final mark for correctly recognising that some areas are positive, some are negative, and combining them correctly to get the 13.8. Moving on to part 3. You got a method mark for showing that you were differentiating, an accuracy mark for correct differentiation, and an accuracy mark for the answer of -12. In part 4, there's just one mark for recognising from the graph, an independent mark, that the velocity for model A is -4 when it's at a minimum. And then on model B, we get a method mark for recognising that the acceleration would have to be 0 at that minimum point. And then an accuracy mark for working out the -4.5. So substituting that value of 3.5 back in. And then a final follow-through mark for making a correct comment in relation to the values that you calculated in the question. So in our case, the correct answer is that there was a 0.5 meters per second difference and model B was 0.5 less than model A. Finally, on part 5, you get one method mark for recognising that we need to be integrating. Accuracy mark for getting 2 or more of these terms correct in the integral. A method mark for subbing in the limits, and a final accuracy mark must be the correct answer there for that final mark. If you'd like to look at any of our other revision videos, go to our website www.furthermaths.org.uk.